This video is an introduction to the idea and the concept of a derivative, and it will address these three main things. And they are, we're going to talk about the difference between the slope of a secant line versus a tangent line. We're going to talk about what the definition of a derivative is, and then answer the question conceptually, what is a derivative? First, going to talk about the difference between a secant line and a tangent line. Now, these are not the trigonometry graphs of tangent and secant. A secant line is basically a line formed using 2 points, and a tangent line is a line formed using 1 point. To illustrate this, let's draw a function. Ta-da! There's a function f. And a secant line has 2 points on the function. There's one, there's another, and connects the 2 points like that. Beautiful. A tangent line, on the other hand, there's our function. 1 point, and the tangent line touches the function at only 1 point like that, and lies in such a way so that the slope of the tangent line here matches up with the slope of the function here. So if you can imagine the tangent line is getting infinitely close to the function, it touches it at one place and it doesn't actually cross the function. It only touches it and then bounces right back off, but it's still a straight line. Let's talk about slope. For a secant line, this is what we're used to. We have 2 points. Let's label them. Traditional labeling is x1, y1, x2, y2. And now to find the slope, we just do the basic difference quotient. y2 minus y1 over x2 minus x1. And this idea is really getting at just it's the change in y over the change in x. Now, to figure out the slope of the tangent line using only 1 point, this is a really big question, and it's not easy. It took people thousands of years to figure out how to do this. Like, this sort of stuff is what the ancient Greeks were doing, but it took until about the 1600s to figure out how to do the slope of a tangent line touching a function at 1 point. Here's how to do it. The first way to think about it is the way that most calculus textbooks teach it. You have a function, f, there it is, and what we're going to do is we're going to take 1 point here, and we're going to call it x comma f of x, because those are the coordinates. And this is the target point as to where we want to get the tangent line. And to do this, we're going to have to draw another point, because that's how we get slope. The only way we know how to find slope right now is to have 2 separate points. So we're going to take this green point, and the coordinates of it are going to be x plus a small change in x, like something small, like delta x. So delta x is just some small thing. And then the y value of this point is f of x plus delta x, like that. So pretty straightforward so far. Hey, we have 2 points, so we're going to draw the secant line in green. There it is, secant. Can't you see it? And then I'm going to find the slope of this secant line. So to do that, we're going to do the change in y divided by the change in x. Let's do it. So we have f of x plus delta x minus f of x, those are the 2 y values, and we're going to divide by the 2 x values. So x plus delta x from the green point minus x. Oh, and notice in that denominator there, you have x and minus x, so we're going to clean that up a little bit. Bam, they simplify to be delta x. Right, now, here's the hard part conceptually. What we're going to do is we're going to take this green point, green, not blue, green, and we're going to move it infinitely close to red. Watch. Starts here, and then it's going to move. Watch it move. Oh my gosh, they are so close to each other. I can't even see what's going on here. Wait for it. I'm going to zoom in on the function. Remember from the first day, what happens when I zoom in onto any function? Notice that this function looks smooth and it's continuous. Watch. Ha! Remember, after a while, I can zoom in close enough where the function, the original function that was curved, I've zoomed in close enough where the original function that was curved now looks straight. Oh, this is so cool. And now, because it's straight, when I find the tangent, or when I find the secant line that goes between the red point and the green point like this, it matches the function almost exactly. And now what we're going to do is we're going to imagine that green point moving close to the red point. And how do we make something move infinitely close to something else like that? Oh, I think we've been studying it for a little while. I think it starts with an L, and I think and I think it ends with imit. That's right. We're going to do the limit. Watch closely. We're back to this page. We have that slope right there. That slope right there. And remember, we wanted to drag that green point infinitely close to the red point. And how do we do that with the variables that we have? Well, x can't really change since it's right there. But look at that. That small thing, that delta x. That's got to go away. And so what we're going to do is we're going to take the limit as delta x goes to 0. And so the slope now becomes the limit as delta x approaches 0 of all the rest of that stuff. And that expression right there is the slope of the tangent line. Wow, that's so cool. I don't remember if I said there was going to be 2 ways, but hey, there's 2 ways of thinking about this. Here's the second way. It's almost exactly the same. Stay with me. You have 2 points, and let's label them. This time, instead of x and delta x and all that weird funky stuff, a little bit simpler. A, f of a, c, f of c. I'm going to set up that slope difference quotient. So if you think about it, all I did was slope, change in y, divided by change in x, f of c minus f of a over c minus a. And now, here's that conceptual part again. Imagine me taking the green point c and dragging it infinitely close to a. And in this case, nothing's getting smaller because there is no delta x that's getting smaller. Instead, we can think of c approaching a. So we're going to take the limit as c approaches a. And here's what this looks like. We can basically tack on limit c approaches a of that. And that's the second expression for the slope of the tangent line. Going back to that first expression really quick. Hey, there it is. And guess what? You need to memorize this. And the reason is because the derivative is so hugely important to calculus that we need to know where it comes from. So this is what's called the limit definition of the derivative. And so the limit definition of the derivative is that the slope of the tangent line equals the limit as x approaches 0 of f of x plus delta x minus f of x all divided by delta x. Whew, that is a mouthful. Let's talk about how we can see this idea represented mathematically. We have these 2 limit definitions. This top one is the one you need to memorize. This is another one if you want to memorize more things. That's okay with me. But here's an easier way of representing this idea, and because writing this all the time would just be obnoxious and take a lot of time. This is written as f, the function, right there, f, and then we put this little thingy on top of it, like an apostrophe, but it's not, it's, yeah, like a quotation mark sort of, I don't know, like that. Okay, that's that one. And then the bottom one, instead of x, we had a, so it's weird symbol F, weird symbol A. And here's how to say these things, because really we need to talk about that normally. The following will be all mathematical acceptable ways to say the following sentence. The derivative of f, or y, with respect to x. Here they are. That's the one we saw before. Here's how we say it. F prime of x, or just f prime for short. F prime of x, or f prime for short. Mentioned before that this was our formula for slope right here. Don't write that down as the derivative, because the derivative has a fancier version, and it looks like this. Wait for it. That's right. dy dx. Notice how I said that? You just say dy dx. People know what you're talking about. Don't say dy over dx, then you sound kind of weird. Dy dx, that's it. Similar to the first one, you can say y prime. Great. Just like that. And then similar to the second one, you can say, or write, d dx of f. And you can say it like that too. d dx of f, or the following, you could always say the derivative of f or y with respect to x. That always works. You do have to know what all of these mean, because they all mean derivative, because I'll use them interchangeably, people will use them interchangeably. Whenever you're in calculus, these will always be interchangeable. So I've done a lot of talking about derivatives, sort of some limit stuff and tangent lines and secant lines, but let's get down to business. What is a derivative? Here are some easy definitions that you should know conceptually and algebraically that we can work with. The first one is obviously the limit definition of the derivative. You need to know this basically to know where a derivative comes from. We'll use this a little bit in class. This kind of stuff can get algebraically nasty, so we'll probably only do a few examples of that, and then there are tricks that are so easy and simple and beautiful that we won't even bother with this for a while. But you need to know what this is, where it comes from, etc. The easiest way I found to explain a derivative is that a derivative is basically slope. They're not technically interchangeable, but they both contain the same ideas of like slope of a secant line. Derivative is the slope of a tangent line. So specifically, a derivative is slope, specifically slope of the tangent line to a function. Last thing that we're getting at is the slope. If you think conceptually about a slope, kind of like change in y over change in x, or dy dx, we're getting at the idea that a slope is a rate of change. And specifically, the derivative is the instantaneous rate of change of a function, like that. Let's compare this really quickly to the, again, going back to the secant versus tangent line perspective. On that secant line, notice, you had 2 points, you took the slope between them, and the slope here is a sort of average of the rate of change because it ignores all this curviness going on in here. Whereas here with the tangent line, okay, you're finding that exact slope. It's taking into account all the curvature of the function, and it's exact, and it's instantaneous because you're only looking at that single point. So that's basically conceptually, with the derivative, you'll hear a lot of words like instantaneous and tangent line and that sort of thing. And we'll see that language used often in calculus. With secant line, you'll hear more words that have to do with average and that sort of thing. So we'll see that as it comes up. Until then, get some questions about derivatives. Think about this, mull this over in your brain, come to class with questions, and we'll be ready to go.